All right, good morning, everyone. So just got a quick recap of what we did on Monday. So again, we introduced the electric force. So we said the electric force is the force between charged particles or charged objects, where the Coulomb's law specifically is the force between point-like charges, so between charged particles themselves. So what this says is that the magnitude of the electric force is equal to K, so this is a capital K, but at least a different K, times the magnitude of Q1 times the magnitude of Q2 divided by R squared, where R is the center-to-center distance between those two charged particles. And then this is going to result in either an attractive force or repulsive force, depending on the relationship between the charges. So if they both have exactly the same sign of charge, so if they're both positive charges or both negative charges, that manifests itself as a repulsive force. And if they have unlike charges, so if one is positive, one's negative, or this one's positive, this one's negative, doesn't matter the order, then that manifests itself as an attractive force. Then we said the superposition is just a fancy word of saying if I have more than two charged particles, if I have 3 or 4 or 5 or an infinite number, then the total net force on one of those particles is simply equal to the sum over all the individual force pairs. So this is just simply the force between charge 1 and 2, 1 and 3, 1 and 4, 1 and 5, et cetera, vector sum all these guys together, and then that is the total force. So basically all we're going to do today is a whole bunch of examples, trying to get a better idea of how all this stuff actually works. So our first example we take a look at is this one. So let's say we have this array of 3 charged particles. So we have Q1 here, which has a charge of negative 86 microcoulombs. So micro is 10 to the minus 6. Q2, which is 50 microcoulombs, and then Q3, which is 65 microcoulombs, which are arranged in this area here. So this is actually supposed to say theta, not check mark. I don't know why I came up with check mark, but whatever. So that's 30 degrees. And what it wants us to find then is what is the total force on Q3? So this is what we want to know. What is the net force on that third charged particle? So let's bring up some artistic skills here. So here is my array. So Q1 we know is out here, so this is Q1. We have Q2 here at the origin. We have Q3 some distance up here, so this is Q3. We know this was what, minus, switch back, minus 86, 50, and 65. So minus 86 microcoulombs, 50 microcoulombs, and 65 microcoulombs. And then we know that this distance here, or at least this angle, is equal to 30 degrees. Put in all the distances. So we know 52, 30, and 60. So this is 52 centimeters, this is 30 centimeters, and this is 60 centimeters. So okay, all we want to know then is what is the net force then on Q3 here? So let's draw our forces then. So what we know is that each one of these guys is going to create a force. So let's first look at the force between Q1 and Q3. So we know Q1 is a negative charge. We know Q3 is a positive charge. So is that an attractive force or a repulsive force? So they're unlike charges. So is that attractive or repulsive? Attractive, good. So in this case, we know that what? The force on 3 by 1 is going to point along the line connecting these guys together. So this is then F31. Now we also know this one is positive, this one is also positive, so then the force on 3 by 2, since these are like charges, is then an attractive force or repulsive force? That's a repulsive force. So this one then has to point in the y direction. So it's going to be our force on 3 by 2. So the net force between the two of those is simply going to be the vector sum, which should point off something like this. So this is going to be our force 3. So it's going to be our total force 3. Good. So from here, we're simply going to move then our coordinate system. So I'm going to move my coordinate system actually to here. So I'm going to call this my x-axis. Continue to call this my y-axis. So that if this internal angle here is 30 degrees, then that means this angle here is also 30 degrees. Remember, alternate interior angles on parallel lines is the same. So this angle here of 30 degrees is the same as this angle of 30 degrees. So good. So now what we know is that what? The net force on 3 is simply going to be equal to the sum of the force on 3 by 1 plus the force on 3 by 2. Now, from here, what we can see is that the total force is going to be a two-dimensional force. Right? There's going to be some of it in the x direction, some of it in the y direction. So from here, we have two choices. Either we can do this in vector notation. So we can write out both the x and y components, and then from there, simply state our vector as something in the x direction plus something in the y direction, i.e. I hat and j hat, right? Usual vector notation. Or we can give the magnitude of the net force and the angle. Either one is sufficient. Doesn't matter which one you want to do. Which one do you want to do? Vector notation or magnitude and angle? I'll let you choose. Which one do you want? What's that? Vector notation. Great. Let's look at vector notation. So this is then going to be equal to, so let's write out each force independently. So here we then have what? F31. So according to that, F31 is this vector which points down in this direction. So this is going to have an x component, which is going to go with the cosine portion here, and then it's going to have a y component, which is going to be a negative sign across here. Right? So let's write it this way. So this is going to be equal to then F31 cosine of theta, I'm going to write it as theta for now, in the I hat direction, plus F31 sine of theta, actually sorry, minus, points in the negative direction, j hat, great. And then we have this force here, which is 3,2, which only points in the j direction. So this is then going to be simply plus F32 in the j hat direction. It's okay? I have to change slides here, so let me rewrite this. So this is F3, then is equal to, so now I'm going to combine components together. So it's going to be F31 cosine of theta in the I hat plus F32 minus F31 sine of the angle j hat. So just combining the components together. Okay? So now Coulomb's law says that F31 though is equivalent then to K times the magnitude of Q3 times the magnitude of Q1 divided by the distance R31 squared between the two, times then cosine of the angle I hat. So here we're just inserting the definition of Coulomb's law. And we get a plus F32, which is then going to be K times magnitude of Q3 times the magnitude of Q2 divided by the distance R32 squared, minus K times then the magnitude of Q3 times the magnitude of Q1 divided by R31 quantity squared, sine of the angle all in the j hat direction. Is it okay? Okay, yesterday we learned that K was equal to 9 times 10 to the 9th Newtons meter squared per Coulomb squared. According to our picture, we now know that what? The distance between 3 and 1 is 60 centimeters, and the distance between 3 and 2 is 30 centimeters. So that means R31 is equal to 0.6 meters, and R32 is equal to 0.3 meters. Now again, the absolute value signs are put in here because we already chose the direction of the forces based off of how they're interacting with each other. Right? So here, I said that this was an attractive force, this was a repulsive force. So if I didn't put the absolute values, I would have to then put in this negative sign, which would switch the direction of this force, which would cause it to move in the wrong direction. So here, just make sure that these signs are put in appropriately. So from here, I simply plug in my numbers. We find then is that F3 then is equal to, let's plug in my numbers. So this should be equal to, get all my numbers correct here. So this will be equal to 120 newtons in the I hat direction plus 260 newtons in the j hat direction. So this is our force. Okay? Not too bad, right? Not too bad. Let's do another example. So the next example says that we have two charged particles that are both fixed on the x-axis. The first charged particle, which has a charge Q1 equal to A times Q, whatever Q is located at the origin. The second one, which has a charge of -3Q, again, whatever Q is located at a distance along the x-axis at a distance of L, to the right of the origin. So then it wants to know, at what points, other than spatial infinity, can a third charged particle, Q3, with a charge of 5Q, be placed so that it is in equilibrium? So let's draw our situation. So example 2. So example 2 says that here is our x-axis. So here's our y-axis. So we're going to put Q1 here. So this is Q1, which is equal to 8 times Q. Q2 is going to be located here, which is -3 times Q, which is some distance of L away from the origin. Now what I want to know is if I have another charge out here, Q3, which was equal to, what, 5 times Q, if I remember correctly, where can I bring this into this configuration so that the total force on Q3 is equal to 0? So what I want to know is where can I place Q3 such that the total force on this thing is going to be equal to 0? It's okay with this? So to do this problem, we can't just arbitrarily say it's going to be somewhere. We have to first figure out where is a location along here where it makes sense that it can be put. Then we can go through the math and actually solve it. So what that means is, naturally, we're going to have 3 locations. I'm going to have either somewhere out here, which is to the left of the origin. I'm going to call that region 1. Region 2, which is going to be the region between Q1 and Q2. And then finally, region 3, which is going to be the right to where Q2 is. And what I want to know is which one of these 3 regions could I put this third charge so that it experiences 0 force? This is what we want to know. What's up there? Good. We'll get there. We'll go through each section and we'll talk about it. But you're correct. So, good. So let's first talk about region 1. Could I put this charge at region 1? What do you think? So could I put the charge in region 1? Why or why not? So meaning, could I dump this charge, use the same color I drew here. So could I put it here? Could I put Q3 here and have it in equilibrium? Meaning that there's going to be no acceleration. Go ahead, Derek. Good, that's right. So the answer is no, and the reason for that is what? Let's look at the force between these 2. These 2 then are both positive charges, which means it's going to result in a repulsive force here. This one is going to also experience a force from him, which is going to be an attractive force, so it may be possible, right? Because here, again, this one's going to feel a force in this direction, so this is going to be F3(1), but it's also going to feel an attractive force in this direction, which is going to be F3(2). But remember that Coulomb force goes as the product of the charges on top divided by the distance squared on the bottom. So what Derek is basically getting at is what? Here I have 5 times 8, which is a large number, but I also have a very small distance now between these 2, which is also going to be a very large number. Which means the size of this force here is going to be very large. Right? I have a large numerator divided by a very small denominator, which makes it a very large number. Simultaneously, I have the force between this one and this one, but now I have 5 times 3, which is a smaller numerator. And this distance from here to here is actually much greater than this distance from here to here, which means it's a much larger denominator, which means now I'm taking a small numerator dividing by a large denominator. What does that do to the size of the force? Makes it small. So ultimately what will happen then is this force is going to be much greater than this force, what will result in a total force pushing in this direction, causing it to accelerate. There is no place over here except at spatial infinity I could put this particle. Okay with this? So automatically that tells me region 1 is gone. I cannot put that there because it's going to result in a repulsive force causing it to accelerate all the way to spatial infinity. Is okay with this? Go. Okay. What about region 2? Could I put this in region 2? Could it go in region 2? Go ahead, Bill. Not quite. Not quite. So let's draw it in region 2 and let's think about region 2. So if it's here in region 2, this force and this force is now going to be a repulsive force again, right? Because they're both like charges, which means the force on him by him is going to be to the right. Right? So the force direction on him will be F31 this way. But simultaneously, this is a positive charge, this is a negative charge, which means what type of force is between these two particles? An attractive force, which means that there's also a force in this direction by F32, which means both forces are pulling in this direction, so what's the particle going to do? It's going to accelerate. So anywhere I put it in region 2, it's going to result in a total force pulling to the right, which means it's only going to accelerate to the right. So you're kind of right, but not exactly by the right reasons. So in this case, the net force acting on 3 will then only be to the right, so this is going to start here and accelerate across to here. Which also tells us this is not correct either. It cannot go in region 2 either. So that means finally the only place that it could go, which is the original place that Derek told me, is to the right. Right? Why is that? Well, again, here, this one and this one are going to give me a repulsive force. So this thing is going to feel a force to the right in this direction. So this is going to be F31. But these are unlike, so that means it's also going to feel a force then to the left, F32. But now what's happening is now I have, again, a large numerator, but now this distance is very large, which gives it a very large denominator, which means I have a large numerator divided by a large denominator. Versus here, I now have a small numerator, but I also have a small denominator, which means that those two will equal each other because the ratios will be the same. So the only place I can put this thing is here in region 3. That's the only place I can put this. So let's define this distance as the distance x. So let's say the distance x away from the origin where I'm placing the charge, Q3, is the distance x. Is okay? Good. So from our free body diagram, what we see in this case then is F31 points to the right, F32 points to the left. So in this case, we can then say that the total force on F3 is then equal to F32 minus F31. And we want this to simply be equal to 0 because we want it to be in static equilibrium. Good. Now, let's use Coulomb's law. So this says that K times the magnitude of Q3 divided by the times the magnitude of Q2 divided by the distance between those two. So that's going to be a distance of what? X minus L, quantity squared, minus then K times the magnitude of Q3 times the magnitude of Q1 divided by the distance X squared must all be equal to 0. So it's okay that this is X minus L. So again, if I go out to X, and I subtract away L, that's this little distance here, so that distance is X minus L. Is okay with that? Good. Now the other thing to notice is that K here is the same, so I can divide that through. Q3 is the same, so I can actually divide that through. So I'm then left with, which pages? This becomes the magnitude of Q2 divided by X minus L, quantity squared, is equal to then the magnitude of Q1 divided by X squared. Okay? Now from here, there's two ways to do this. We can either first cross multiply and then square this out, and then eventually we'd have to solve a quadratic equation. But we don't want to do that, we're lazy, right? So it's an easier way to do that. The easier way to do that is simply take a square root of both sides. I take a square root of both sides, that's going to get rid of the square root. So now I have the square root of the absolute value of Q2 divided by x minus L is equal then to the square root of the magnitude of Q1 divided by x. So now we can cross multiply and then solve for x. So let's go ahead and do that. So we get the square root of Q2 magnitude times x is then equal to the square root of magnitude of Q1 times x minus the square root of the magnitude of Q1 times L. So here we're going to add what? This term over here, subtract this term, factor out the x, and then divide. So finally we get x then is equal to the square root of Q1 magnitude divided by the square root of Q1 magnitude minus the square root of Q2 magnitude all times L. Looking at numbers, what we find in this case is this works out to be about 2.58 times the length of L. So that's using the fact that what this guy is 8, and then this one was what? 3, right? Yeah. Right? Not too bad. So before I move on, let me just go back here. Is everybody okay with these arguments? Line, they can't go in these different locations. Everybody's okay. Good. Okay. Let's do another example. Next example then says that we have two positive charges of capital Q are affixed rigidly to the x-axis at locations D and negative D. A third charge of charge little q and a mass of m, which is constrained to move only along the x-axis, is displaced from the origin by a small amount of x much, much less than d, and then released from rest. So let me draw the picture before I want to go on from it. So let's draw a picture first. So here's my x-axis. Here's my origin. So this is y. So it's saying I have one charge here, where this is charge capital Q. So this is a distance of d. I have the same charge over here, Q, which is at the same distance of d. So now what I'm going to do is I'm going to take another charge, little q, and I'm going to put it at the origin. So when it's at the origin, how much force does it feel? 0. Exactly. So what's going to happen is all three of these, let's say they're all positive charges, so this one's going to push it away this way, but this one simultaneously is going to push it away this way. But since they're the same distances and the same charges, then the total force acting on it has to be 0. Great. But now what I'm going to do is I'm going to take that same charge and I'm going to displace it a little tiny distance here, x, where this x is much, much less than d. So what happens if I displace it to the right? Well, if I displace it from the right away from the origin, what will happen then is the force between these two charges will now be greater than the force between these charges, which means the repulsive force between these is less than the repulsive force between these, which means this thing is going to start to accelerate back to the origin. Okay. As it accelerates to the origin, what becomes the acceleration at the center? Well, Dylan already said 0 because the net force is equal to 0, which means it's going to have too much velocity, so it's going to carry through, and then now this force between this one and this one becomes greater than the force between this one and this one, which means it's going to slow down and stop, but now it has a maximum acceleration, so what's it going to do? It's going to accelerate back in this direction, and it's going to repeat the process, which means the particle is going to do what? Harmonically oscillate back and forth. I love harmonic oscillation. Okay, so great. So this problem then is asking us, what is the harmonic oscillation of this particle? That's what it's asking us. So let's go back to the problem. So then it says, determine an expression for the angular frequency and its oscillation period. I'm sorry. I skipped the part. And he says, show that it will execute simple harmonic oscillation. We already said it does, so great. Part B then is the determinant expression for the angular frequency as well as the oscillation period. Then part C says, if these charges are singly ionized sodium atoms, which have the mass of sodium atoms, but since they're singly ionized, that means they have a charge of the charge of an electron. So all three of them have the charge of an electron. And at the equilibrium spacing of the typical atom size, which is about 3 angstroms, find the period in picoseconds. So if this was the sodium atom, I have another sodium atom in between, I displace them, that thing is going to harmonically oscillate. So we want to know, what is the period in picoseconds? Anybody know what picosecond is? 10 to the minus what? What's that?
12.
12, good. So picosecond is 10 to the minus 12. Good. Great. So first thing we want to do is show that this thing harmonically oscillates. So let's assume that it is here. So this is our displacement x. So here I'm going to write this slightly differently. So what I'm going to say is that this one is charge right, and this one is charge left, just so we know which one we're actually talking about. Now we already know that Q and Q are the same, but just so we know which one is which, we're going to write out the forces, right? Now again, our force from Q right is going to be in this direction. So this is force Q right. And then our force Q left is going to be in the opposite direction. So let me use a color I haven't used yet. We'll use yellow. So the force on him going in this direction is going to be force left. Just write it left and right. There we go. Force right and force left. So in this case, the force from the left is going to be pushing to the right. The force from the right is going to be pushing to the left. Right. So let's do that. So here we can then say that what? The sum of the forces on Q then is going to be equal to force left minus force right, and that must be equal to Newton's second law, which is the mass times the acceleration. Now, force left, though, we know is equal to what? K times Q left times Q, divided by the distance between those two. Well, the distance between those two then is going to be what? This total distance here. So this total distance then is going to be the distance d plus the distance x. So this is going to be then, actually, sorry, I have my negative signs in the wrong spots. There we go. No, I was right the first time. Sorry. Ignore what I just said. Okay, there we go. Good. So this distance then is going to be what? D plus x squared. Good. Minus force from the right, which is then going to be Q right, Q times K divided by this distance. But the distance between these then is going to be the distance D minus that distance x. So this is then going to be D minus x quantity squared. And that must all be equal to mass times the acceleration. Okay? Now at this stage, we're going to use the fact that we know QL is equal to QR, so this is just Q, and we're going to go ahead and factor all that stuff out. So finally, what we can write then is that MA is equal to K times Q times 1 over D plus X squared minus 1 over D minus X squared. Now from here, we have a common denominator, and that common denominator is simply the product of both of these two. So this is going to be equal to KQQ times D minus X squared minus D plus X squared, all divided by D plus X squared times D minus X squared. So good. So now let's square these two terms out. I'm going to do that over here. So if I do D minus X quantity squared, that's the same thing then as what? D squared plus X squared minus 2 times D times X. And then D plus X squared is equal to D squared plus X squared plus 2dx. So now, if I take this guy minus this guy, what happens? Well, the d squareds are going to cancel. The x squareds are going to cancel. But now I get a negative sign between the two of these, which means these guys are actually going to add together. Right? So everything is going to cancel except for the cross terms. Is okay? So switch pages again on it. So now I get MA then is equal to K cubed Q times minus 4, because I get 2 of those, times D times X divided by D plus X squared times D minus X squared. We're almost done. Now from here, the problem stated that we're going to displace X much, much less than D. Okay? Which basically means we have 2 options here. Since X is much, much less than D, we can either do this the proper way, which would be Taylor series expand the denominators, which would be awesome and fantastic, but we're not going to do that. Or we're going to do it a simpler way and say, well, if D is much, much greater than X, what is D plus X then? So if D is much, 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 much greater than X, what is D plus X? It's just D, right? And if I have D minus X, which is D is much, much, much bigger than X, what is D minus X then? Just D, right? So basically, these 2 denominators are approximately then just equal to D. So this is going to be D squared and this is going to be D squared. Which means that the denominator here is actually simply just going to be D squared times D squared, which is D to the 4th. So finally, I can write this as minus 4 times K times Q, but then this D is going to cancel out with one of these, divided by then D cubed, all times X. Because again, this is going to be D to the 4th, but I have a D on top, so that D is going to cancel out one of those, which is going to make it a D cubed. Okay? Finally, what we said was what? To determine the angular frequency, we had to isolate the acceleration, which means we simply have to divide both sides by the mass. Once I divide both sides by the mass, I'm going to get the acceleration by itself. So let's do that. So this is the acceleration then. I'm just going to put the m on the bottom. So this is then our acceleration. So remember, as we said last test, once we have the acceleration, whatever shows up behind the negative sign and in front of the x is the angular frequency squared by definition. So this says that our angular frequency is simply equal to the square root of 4 times K times Q divided by md cubed. We then know our period is equal to 2 pi divided by the angular frequency. So it's going to be 2 pi times the square root of md cubed divided by 4k cubed. So this is part A. Part A is to show it that the acceleration is that of simple harmonic oscillation. From there, for part B, we can then simply read off what is the angular frequency and then read off what is the period. Okay? I'll do this a lot just to haunt you with harmonic oscillation because we can't forget about it just because it's not here anymore. Put this in a little bit of context. This was an exam question at one point, but I took it away. So now we just do an example in class. Not to scare you. Everyone's okay? Good. So finally, part B or part C then says, now let's put some numbers. So now we know that the distance D is what, an angstrom or like 3 angstroms. Yeah, 3 angstroms. We know the charge, both charges are simply E, and we know the mass of the sodium. So all we're going to do then for part C is take those numbers and put them into our period expression. So our period expression then, after plugging in our numbers, becomes, so this works out to be about 0.24 picoseconds. So that's the period. So the period of oscillation is 0.24 times 10 to the minus 12 seconds. Is it okay? Not too bad. Let's do one more. So the last problem then says that we have charge Q on a tiny sphere, and then we're going to touch that sphere to a second sphere, which the second sphere has an original charge of 0. So we want to know then how much fraction of our charge is transferred from the one sphere to the other sphere. And more particularly, we want to know what fraction of that charge is transferred so that the force between the two spheres is now maximum. Then we want to know what fraction, the smaller fraction and the larger fraction, would put the force between the two at half of the maximum. So let me kind of draw what's happening here. This will make a little more sense. So I'm starting off with a sphere, which has a total charge of Q. I have a second sphere, which has a total charge of 0. This one has 0 charge. Then what I'm going to do is I'm going to touch these two together so that some of the charge from this one gets transferred to this one. Okay? So basically meaning that what will happen is, once I pull them apart, this one now has a fraction of the charge alpha Q, where this one then has 1 minus alpha times Q charge left. Okay? So the amount of alpha Q went to this one, then this one is left with 1 minus alpha Q. Okay? Now what part A is saying is we want to know what is the value of alpha such that the force now between these two spheres, which we can pretend are point charges, maximizes the amount of force. Okay? So let's look at one of these guys. So what this is going to do is it's going to result in a repulsive force. So this is our force, where the force then is going to be equal to K times the charge on the first one, which is 1 minus alpha times Q, times the charge of the second one, which is alpha times Q, divided by the distance d squared between the two. We're simply saying this distance then is d. Okay, so this is the force between the two. Now again, what we want to do then is determine the amount that we have to put on, or take off of this one and put onto this one, which is going to extremize this amount of force. So, how do we extremize a function? Go for it, Corey, you're smiling.
I'm smiling because I did not get that on the exam. You take the derivative.
You take a derivative, that's right. Yeah, you cracked me up on your exam, you just said calculus. That's right, exactly. We use calculus. We do a derivative. That's right. Anytime we want to extremize a function, we take the derivative of the function in respect to the thing that we want to extremize. In this case, we want to extremize alpha, so we're going to take the derivative of the force with respect to alpha. So we need to take df d alpha, and then what do we do with it? So we take a derivative, that's right, and then we do what? I heard somebody mumble. Set it equal to 0, great. Or we sit back and just admire ourselves for taking a derivative. Right? One of the two. So we take a derivative, we set it equal to 0, and then we solve for that value of alpha. Right? That is going to be the one that extremizes our function. So let's do that. So this is then equal to the derivative with respect to alpha of K 1 minus alpha times Q times alpha times Q divided by the distance d squared. Right? Now let me ask you a question. What's the derivative of the constant with respect to alpha? 0, right? So basically what should happen then is K is a constant, Q is a constant, Q is a constant, d squared is a constant, so all those things come outside of the derivative because we just don't. So this is equivalent then to K times Q squared divided by D squared times the derivative with respect to alpha of alpha minus alpha squared. Okay? Now, since all this is equal to 0, do I care about any of this stuff? No. This is all equal to 0, which means I can divide all this stuff over here, which means all this stuff is gone. Go away. So finally what I have is 0 then is simply equal to the derivative with respect to alpha of then alpha minus alpha squared. What's the derivative of alpha with respect to alpha?
1 minus 2 alpha.
What's that?
1 minus 2 alpha.
You did the whole thing, but yes. So derivative of alpha with respect to alpha is simply 1. So this is 1 minus 2 alpha. Good. Exactly. So this means that the value of alpha, which extremizes our function, is simply a half. Okay? So what this means then is for the force between the two to be the greatest amount of force, the one sphere has to give up exactly half of its charge to the other one to then have the greatest amount of force. That's what this thing is telling us. So the force to be the greatest between the two has to give up exactly half of its charge to be the greatest amount of force. Good. So that's it. So we know for part A, alpha then must be equal to 1/2. Now from here, we can then determine what is the maximum force. So the maximum force then is going to be equal to, well, K times Q squared times 1 minus alpha times alpha divided by D squared, where again, we're going to evaluate this at alpha is equal to 1/2. So I get 1 minus 1/2 times a half, so that's a half times a half, which is a fourth. So finally, this says that the maximum amount of force is equal to 1/4 K times Q squared divided by D squared. So this is the greatest force. Now, what part C and D are now saying is, well, what we actually want is the amount of charge which is transferred, which is half of the amount of this force. Okay, so what I want to know is how much charge must be transferred from one to the other one to make a force which is half the size of this. This is what C and D are saying. Or is that B and D? Or B and C? I think B and C. So let's do B and C together. Great. So what we want now is that the actual force then is equal to 1/2 of the maximum force, which is then equal to 1/8 of K times Q squared divided by D squared. And that's then equal to K times Q squared times alpha minus alpha squared, all divided by D squared. So this is the actual force, which is this one. So that's KQ squared, alpha minus alpha squared divided by D squared. And that has to equal half the maximum force, but this is the maximum force, so half of that is 1/8. Is okay? Good. Now from here, the K's are the same, so we can cancel those. The Q squareds are the same, so we can cancel those. The D squareds are the same, so we can cancel those. So finally, what we get then is that 1/8 is equal to alpha minus alpha squared. So finally, this thing says then that we can write this as alpha squared minus alpha plus 1/8 is then equal to 0. So to solve this, all we have to do then is solve a quadratic. From our quadratic, what we find in this case then is that alpha, so alpha then is either equal to, let's write it out this way, 1/2 of 1 plus or minus the square root of 2 divided by 2. So that means then that alpha large is then going to be 1/2 of 1 plus the square root of 2 divided by 2. So this is alpha large. And then alpha small is going to be 1/2 of 1 minus square root of 2 divided by 2. So these are the two different alphas. So this is actually the answer to part B, and this is the answer to part C. So these are the amount of charges which has to be distributed to make sure that the force is half of that maximum force. Okay? So a lot of these examples we're going to be doing, especially in this chapter, will all be algebraic, because we're going to be doing a lot of integrals and things like that. So hopefully everybody just loves algebra from here on out. So like, will be great. So that's it. We're done with all the examples for today. So tomorrow, we're going to start talking about something more abstract, which is the electric field. Okay. Now, having said that, I have our exams. I think it was great. They didn't turn out as great as I wanted. Just kind of be honest about that. So the average was about a 58. A little after extra credit, it jumped up to about a 68. which is better, you know. So I compared it to last year. So their average was like almost a 70. But the year before that, their average was like a 65. So you're doing better than 2 years ago. So that's a good part. All right. So now the only complaint I'll basically say is don't write crap down on your equation card if you don't know what it means. Too many people I saw write down that the velocity of the string was equal to the square root of the tension divided by the linear mass density, and then they use that the tension was the period because hell, it's a T. Right? So just don't write things down without knowing what it is, what it's used for, and what all the ingredients of that thing is, because it's the same thing as if you're trying to bake a cake and you put in, I don't know, say citric acid instead of sugar. It's an S. Who gives a shit, right? You have to know what these things are, otherwise it just don't work very well. But other than that, it was reasonable. It wasn't too bad. Like I said, I was hoping for a little bit better, but it is what it is, so it's fine. So like I said, that's my biggest complaint. Other than that, everybody have a great day. I'll see everybody tomorrow. So the highest was an 86 before extra credits. And then with extra credit, the highest was 102. So that is 6 out. Oh. So crappy about that. You have to fill in. Why not? All right, so I'll see everybody tomorrow. What's up? Yes. Oh, I would just draw the rock. I think we worked on it. Yeah, I usually tell everybody to draw it in there because I didn't actually write all that. Okay.